There's something unsettling about the idea that the universe might be keeping secrets from us, especially when those secrets involve stars that refuse to follow the rules. Picture a supernova, one of the most violent and energetic events in the cosmos, exploding with enough force to outshine entire galaxies. Now imagine that same supernova doing something impossible, defying the laws of physics as we know them. These aren't just hypothetical scenarios. Across the universe, astronomers are documenting supernovae that behave in ways that shouldn't exist, leaving even the most brilliant minds in astrophysics utterly baffled. What happens when the very stars we rely on to understand the cosmos start betraying the fundamental principles that govern them? Take the case of a supernova that burns too bright for too long, or another that flickers in a pattern no model can predict. These aren't just minor discrepancies, they're cosmic anomalies that threaten to upend our understanding of how stars live and die. Scientists have spent decades refining their theories, building elaborate models to explain the life cycles of stars, only to have nature throw them a curveball. Some of these supernovae emit energy bursts that defy explanation, while others leave behind remnants that shouldn't be possible. It's as if the universe is playing a game where the rules keep changing, and we're only just beginning to realize how little we truly know. So what's really going on? Are we missing something fundamental about the way stars explode? Or could there be entirely new physics at play, forces and phenomena we haven't even discovered yet? This isn't just about solving an academic puzzle. The answers could reshape everything from our understanding of dark matter to the very fabric of space-time itself. In this video, we'll journey into the heart of these stellar mysteries, exploring the most perplexing supernova ever recorded and the cutting-edge theories scientists are scrambling to test. From bizarre light curves to unexplained energy signatures, these cosmic outliers are more than just oddities, they're clues waiting to be deciphered. And by the end, you might just find yourself looking at the night sky a little differently, wondering what other secrets the stars are hiding. A supernova is supposed to be the universe's grand finale, a star's explosive last act scripted by the laws of physics. When a massive star runs out of fuel, its core collapses in a fraction of a second, triggering a shockwave that rips the star apart in a blaze of light and energy. These explosions are so powerful they can outshine entire galaxies for weeks, scattering elements like iron, gold, and uranium across space, the very building blocks of planets and life itself. For decades, astronomers have relied on these cosmic fireworks to follow a familiar playbook: a sudden brightening, a predictable peak, and then a gradual fade. But lately, the universe seems to be rewriting the script. Take Supernova 2018 COW, for example. Discovered in June 2018, it didn't just brighten and dim like a typical supernova, it flared up in a matter of days, reaching peak brightness faster than any model predicted. Then, instead of fading smoothly, its light curve twisted into jagged peaks and valleys, as if something inside the explosion was fighting for control. Spectroscopic data revealed another shock. The supernova was rich in hydrogen, a gas that should have been stripped away long before the star died. It was like finding a fossilized dinosaur with fresh blood still in its veins, a glaring contradiction to everything we thought we knew. Or consider the case of so-called zombie stars, supernova, that somehow survived their own destruction. In 2014, astronomers spotted a star that exploded, faded, and then inexplicably flared back to life months later. Normally, a supernova leaves behind either a dense neutron star or a black hole, but this one seemed to defy death entirely. Some theories suggest these stars might be tapping into hidden energy reserves, perhaps from a previously unknown type of nuclear reaction or even interactions with dark matter. But the truth is, no one really knows. These aren't just isolated oddities, from supernova that shine too brightly to those that flicker like faulty light bulbs. Each anomaly chips away at the foundations of astrophysics. The real puzzle isn't just why these stars misbehave, it's what their rebellion reveals about the gaps in our understanding. Could there be exotic forms of matter at work, or undiscovered forces shaping these explosions? Every time a supernova breaks the rules, it forces us to question whether we've been reading the universe's playbook all wrong. And that's what makes these cosmic outliers so thrilling. They're not just failures of theory. They're clues pointing toward something deeper, something we haven't even begun to imagine. Some of the most mind-bending cosmic mysteries come from supernova that simply shouldn't exist, stellar explosions so powerful they rewrite the rulebook. Imagine a standard supernova, already one of nature's most violent events, suddenly dialed up to 100 times its normal brightness. These aren't theoretical possibilities. Astronomers have catalogued real supernova radiating with impossible energy, outshining their peers by orders of magnitude while leaving scientists scrambling for explanations. Dubbed superluminous supernova, these cosmic monsters defy every model of stellar death we've painstakingly built over decades. The puzzle begins with their sheer luminosity. A typical supernova peaks around -19 magnitude, bright enough to briefly outshine its host galaxy. But superluminous variants can blaze at -22 or even higher, visible across billions of light years. What could possibly fuel such extreme fireworks? One leading theory points to magnetars rapidly spinning neutron stars with magnetic fields trillions of times stronger than Earth's. If a dying star's core collapses into one of these ultramagnetic monsters, the resulting energy might supercharge the explosion beyond normal limits. But here's the catch. Even magnetar-powered models struggle to explain the brightest examples. Some of these events release more energy in months than our Sun will over its entire 10 billion-year lifetime. Then there's the pair instability hypothesis, a dramatic process where conditions in a supermassive star's core become so extreme that light itself starts converting into matter. This runaway reaction could trigger a total stellar disintegration, leaving behind no black hole or neutron star, just an unimaginably bright fireball. The catch: pair instability supernova should only occur in pristine, early universe stars with virtually no heavy elements. Yet we've spotted modern-era examples, like supernova 2007 Bi, which displayed all the hallmarks despite belonging to a chemically enriched galaxy. Perhaps most intriguing are the outliers that fit no known category. Take supernova 2006 Ji, a cosmic oddball that brightened unusually slowly, lingered for years, and emitted peculiar chemical signatures. Or supernova 2015 L, which produced a light curve resembling a roller coaster rather than the smooth rise and fall of normal explosions. Each of these anomalies whispers the same unsettling possibility, that our current physics might be missing entire chapters on how stars die. Could undiscovered particles be at play? Might dark matter interactions be altering stellar cores in ways we can't yet detect? Every unexplained flash in the distant cosmos isn't just a scientific inconvenience, it's a potential doorway to new physics waiting to be pushed open. And until we do, the universe's brightest explosions will keep burning with questions no one can yet answer. One of the strangest puzzles in modern astronomy isn't about what we can see in the aftermath of a supernova, it's about what vanishes without a trace. When a massive star explodes, it should leave behind some kind of cosmic fingerprint, a rapidly spinning neutron star, a black hole's gravitational shadow, or at least the glowing debris of its shattered outer layers. But in a growing number of cases, astronomers point their telescopes at the heart of a supernova remnant only to find nothing, just empty space where a star once burned. It's like investigating a crime scene where the victim's body has mysteriously disappeared, leaving detectives with nothing but questions. Take Supernova 2005 GL. This explosion in the galaxy M85 was bizarre from the start, unusually dim for a supernova, with a light curve that faded far too quickly. But the real shock came when researchers combed through archival images of the same spot taken before the explosion. There was no trace of a massive star, the kind that should have triggered such an event. It's as if the supernova appeared out of thin air. Similar cases like Supernova 2008 HLS deepened the mystery. Here, pre-explosion Hubble images showed only a faint, elderly star far too small to produce a core collapse supernova on its own. Where did the actual progenitor star go? Did it simply vanish before detonating? The leading theory suggests these stars might have collapsed directly into black holes without the usual fireworks. Normally, when a massive star's core implodes, the outer layers rebound in a spectacular explosion. But if the core is exceptionally heavy, perhaps due to rapid rotation or unusual composition, it could theoretically bypass the supernova stage entirely, swallowing itself whole. The result, a black hole forms in near silence, leaving no expanding debris cloud or pulsar behind. It's the cosmic equivalent of a building demolishing itself without any rubble. But even this explanation has gaps. Some missing progenitor supernova show chemical signatures hinting at violent explosions, contradicting the quiet collapse idea. That's led to wilder hypotheses. Could dark matter be involved, somehow destabilizing stellar cores from within? Or might these stars have been encased in thick shrouds of dust, hiding their true nature before exploding? The most unsettling possibility is that we're witnessing an entirely new death mechanism for stars, one where the rules of collapse and explosion don't apply as we've always assumed. Every time astronomers encounter another progenitor less supernova, it chips away at our confidence in stellar evolution models. These aren't just isolated glitches, they're potential evidence that the universe harbors stellar fates we haven't even imagined yet. And until we solve the riddle of the vanishing stars, every supernova we observe will come with an unspoken question. Will this one leave a corpse behind, or will it, too, disappear without a trace? If supernova were fireworks, most would be over in a brilliant flash, but the universe has a way of keeping us guessing. Among the most baffling stellar oddities are supernova that refuse to follow the script, lingering in a twilight state between explosion and survival. These delayed detonations flicker like candles in the cosmic wind, sometimes for years, as if the star itself can't decide whether to live or die. While typical supernova blaze to life in weeks, these slow-motion explosions unfold at a glacial pace, challenging everything we know about stellar death throes. Take Supernova 2014 C, a cosmic spectacle that defied expectations. Instead of fading after its initial explosion, it brightened again months later, as if something had reignited the blast from within. Spectroscopic data revealed a shell of hydrogen-rich material ejected years before the final explosion, a clue that the star had been shedding layers in fits and starts long before its demise. It's like watching a dynamite fuse sputter unpredictably, sometimes flaring, sometimes nearly going out before finally reaching the payload. What could cause such erratic behavior? One theory points to violent turbulence in the star's core, where chaotic currents might disrupt the collapse, stretching the explosion over years instead of seconds. Then there's the case of Supernova Imposters, events like Eta Carinae's great eruption in the 1840s. where a star brightened dramatically but never quite crossed the threshold into full supernova. These stalled explosions leave behind bizarre remnants, like stellar zombies half alive in their own wreckage. In 2009, astronomers witnessed a star dimming and brightening erratically for nearly a decade before finally erupting. The leading explanation, a deadly tug of war between gravity and radiation, where the star's outer layers teeter on the edge of collapse, held back by immense magnetic fields or the gravitational pull of an unseen companion star. The most tantalizing possibility involves binary systems. Imagine a massive star orbiting a dense partner, perhaps a neutron star or black hole. As the dying star expands, its companion might siphon away material, destabilizing the core and triggering a fragmented explosion. This could explain why some supernovas seem to explode in stages, like a bomb with multiple triggers. Others propose even wilder ideas: quantum fluctuations in the star's core, or pockets of dark matter altering the physics of collapse. Whatever the cause, these delayed detonations reveal a universe far more complex than our textbooks suggest. Stars don't always die in a single, catastrophic instant. Some fade in and out, fighting against their own demise. And with every flickering supernova we discover, we're reminded that the cosmos still holds secrets no model can yet explain. The question isn't just how stars die, it's whether we've been underestimating how strangely they can cling to life. For centuries, astronomers pictured supernova as perfect cosmic spheres, stars exploding outward in all directions with mathematical precision. But nature has a way of breaking our neatest assumptions. Recent observations have shattered the myth of symmetrical stellar deaths, revealing explosions that look more like cosmic shrapnel than orderly fireworks. These lopsided blasts spray debris in chaotic jets and plumes, leaving behind uneven remnants that defy simple explanations. If supernova were snowflakes, no two would look alike, and that's forcing scientists to rewrite the rules of stellar demise. Take Cassiopeia A, one of the most studied supernova remnants in our galaxy. Instead of a smooth, expanding shell, its debris forms jagged filaments and bullet-like clumps racing outward at different speeds. Some chunks of stellar material hurtle at nearly 10,000 miles per second, while others lag behind as if caught in invisible currents. This isn't just random disorder, it points to fundamental asymmetries in the explosion itself. Imagine lighting a stick of dynamite where one end burns faster than the other. The resulting blast would send fragments flying unevenly. That's essentially what's happening inside dying stars, but on a scale that dwarfs human imagination. What could cause such violent imbalance? One leading suspect is rapid stellar rotation. As a massive star nears death, its core spins faster and faster, like a figure skater pulling in their arms. If this spin becomes extreme, the collapsing core might flatten into a disk or even fracture, triggering an explosion that erupts more powerfully along the star's equator than its poles. Magnetic fields could add another twist, literally. Intense magnetic forces might funnel the star's dying energies into focused jets, creating the cosmic equivalent of a squashed firework. Then there's the wild card of binary companions. Many massive stars orbit partners, sometimes another star, sometimes a black hole or neutron star. As the doomed star begins to collapse, its companion's gravity could distort the explosion, pulling debris into lopsided plumes. Some theorists even suggest these hidden partners might steal material from the dying star's core, creating voids that make the implosion inherently unstable. It's like trying to demolish a building where someone's secretly removed key support beams. The collapse would be anything but orderly. The implications ripple far beyond stellar astronomy. Asymmetrical supernova complicate how we measure cosmic distances. since lopsided explosions emit light differently depending on our viewing angle. They also challenge our understanding of how heavy elements spread through galaxies. If debris flies unevenly, some regions of space might get richer deposits of gold or uranium than others. Most tantalizingly, these cosmic irregularities might help explain why some supernova leave behind bizarre remnants like black holes spinning at impossible speeds or neutron stars rocketing through space like celestial cannonballs. Perhaps the most humbling lesson is this: the universe has no obligation to conform to our models. For all our equations and simulations, nature keeps reminding us that chaos is its own kind of physics. Every asymmetrical supernova isn't just a puzzle to solve, it's a masterclass in cosmic creativity, showing us how much we still have to learn about the violent, beautiful deaths of stars. When a star explodes, it's supposed to act like the universe's ultimate alchemist, transforming simple elements into heavier ones through the fiery crucible of nucleosynthesis. Hydrogen fuses into helium, helium into carbon, and so on up the periodic table, forging everything from the oxygen we breathe to the iron in our blood. But scattered across the cosmos are supernovae that break this elemental recipe, leaving behind chemical signatures so bizarre they read like cosmic typos. These aren't just minor measurement errors, they're full-blown contradictions to the established laws of stellar chemistry, suggesting either our models are incomplete or the universe has secret laboratories where elements are made in ways we've never imagined. Consider Supernova 2022 UWA, a recent explosion that left astronomers scratching their heads. Its spectrum revealed bizarre amounts of neutron-rich isotopes like strontium-89 and zirconium-96, elements that typically form in trace quantities during supernova. Yet here they appeared in overwhelming abundance, as if some unseen process had flooded the star's core with extra neutrons at the moment of detonation. One theory suggests these anomalies might stem from collapsars, rapidly spinning dying stars where conditions mimic the extreme environments of neutron star mergers. In these swirling maelstroms, atoms could be bombarded by neutron winds so intense they warp normal nucleosynthesis pathways entirely. Then there's the mystery of supernova rich in radioactive titanium-44, an isotope usually associated with the ashes of white dwarf explosions. When this material turned up in the remnants of core collapse supernova, events caused by entirely different stellar death, it forced physicists to reconsider how elements form under extreme pressures. Some simulations now propose that shockwaves in these explosions might briefly create conditions similar to the early universe, allowing exotic nuclear reactions that bypass conventional steps. It's like discovering a factory that can produce gold without mining just by rearranging atoms in ways we thought were impossible. Even stranger are the cases where expected elements go missing entirely. Take Supernova 2014 J, which produced puzzlingly low amounts of nickel-56, the radioactive fuel that normally powers a supernova's glow for months. Instead of fading gradually, its light curve dropped sharply, as if someone had cut the engine mid-flight. The leading explanation: the star's core might have collapsed directly into a black hole before producing its usual radioactive payload, effectively short-circuiting the nucleosynthesis process. But that raises another question. If black holes can swallow elements before they're fully forged, could entire chunks of the periodic table be vanishing into cosmic voids without a trace? The most tantalizing anomalies involve elements that shouldn't exist at all. In 2017, researchers studying the remnant of Supernova 2006 J detected spectral lines matching no known earthly element. Some speculated it might be evidence of island of stability, super-heavy elements, theoretical varieties with proton counts far beyond what our labs can produce. While controversial, the finding hints at a provocative idea that the most violent stellar deaths might be cooking up matter we've never even classified. What makes these chemical outliers so revolutionary isn't just their defiance of textbooks. They're forcing us to rewrite the story of where matter comes from. If supernova can produce elements through hidden pathways, it means the universe's elemental diversity, the very stuff of planets and life, might be far richer than we've dared to dream. Every anomalous spectral line is a clue pointing toward nuclear physics we've yet to discover, and until we decode them, we're left with a humbling truth. The periodic table, for all its apparent completeness, might still have blank spaces waiting to be filled by the cosmos's most rebellious stars. If there's one rule in stellar physics that seems unbreakable, it's that stars get exactly one grand finale. Like actors taking a final bow, supernovae were thought to be singular, irreversible events, a star's last act before fading into cosmic history. But the universe loves nothing more than to shatter our certainties. Across distant galaxies, astronomers are documenting celestial objects that appear to explode not just once, but multiple times, as if the cosmic script has suddenly allowed encores. These so-called recurrent supernova don't just bend the rules of stellar evolution, they crumple them up entirely, forcing us to reconsider what we thought we knew about how stars live and die. Take the case of Supernova 2014C. This wasn't just a one-and-done explosion. After its initial flare faded, the star, or what was left of it, brightened again months later, as if reignited by some unseen cosmic hand. Then there's the bizarre object known as IPTF14 HLS, which erupted in 2014, dimmed, and then exploded again in 2015 with nearly identical brightness. Over the next 3 years, it flared at least 5 more times, like a stellar phoenix refusing to stay dead. Each outburst released enough energy to qualify as a full supernova, defying every model that says stars can't stockpile that much explosive potential. So what's really happening? One compelling theory involves stellar cannibalism binary systems where one star siphons material from its companion, building up explosive potential over centuries. Imagine a white dwarf slowly stealing hydrogen from a neighboring star until it reaches critical mass, triggering a thermonuclear blast. But instead of destroying the thief entirely, the explosion might eject just enough material to leave the core intact, setting the stage for another theft and another explosion decades or centuries later. It's the cosmic equivalent of a bank robber who survives their own heist to steal again. Then there's the zombie star hypothesis, the idea that some supernova only partially destroy their host stars, leaving behind a reanimated core that can erupt again under the right conditions. These stellar undead might draw energy from hidden reserves, like radioactive material deep in their cores, or from the gravitational pull of a nearby companion reigniting nuclear fusion in their ashes. Some researchers even speculate about more exotic possibilities, stars interlaced with strange matter, their very atoms reconfigured by quantum oddities we don't yet understand, allowing them to detonate in cycles rather than single bursts. The most mind-bending explanations venture beyond known physics. Could these recurrent explosions be tapping into dark energy or other mysterious forces permeating space? Might they involve primordial black holes or other relics from the early universe, objects that could destabilize stars in ways our models can't predict? Every time one of these cosmic repeat offenders flares up, it chips away at the neat categories we've created for stellar behavior, reminding us that the universe's imagination far exceeds our own. What makes these recurring explosions so revolutionary isn't just their defiance of astrophysical textbooks. they're forcing us to rethink the very definition of stellar death. If a star can explode multiple times, does death even mean what we thought it did? Are we witnessing not final acts, but transformations, stellar metamorphoses where one form of existence gives way to another? Until we solve the riddle of these cosmic encores, every supernova we observe will come with a new question. Is this truly the end, or just the latest scene in a much longer cosmic drama? At the far edge of cosmic violence, where ordinary supernovas seem almost tame by comparison, there exists a class of stellar explosions so ferocious they redefine the word extreme. These are the supernova that don't just break records, they obliterate them, unleashing energy bursts equivalent to hundreds of standard explosions packed into a single cataclysmic event. Imagine the sun's entire 10 billion-year energy output compressed into weeks or even days, channeled through jets of plasma moving at nearly the speed of light. These aren't theoretical possibilities, they're real, observed phenomena that leave even veteran astrophysicists stunned and scrambling for explanations. Take the case of Supernova 2005 AP, one of the most energetic stellar detonations ever recorded. Located in a galaxy 4.7 billion light-years away, it shone with the brightness of 100 billion suns, outmatching its peers by an order of magnitude. But what made it truly bizarre were the accompanying gamma-ray jets, narrow beams of ultra-high energy radiation typically associated with colliding neutron stars, not dying stars. This wasn't just a supernova, it was a hybrid monster blending traits from multiple cosmic disasters into one incomprehensible event, the leading suspect behind such extreme energy. Hypernova supernova on steroids, thought to arise when exceptionally massive stars collapse into black holes. Unlike typical core collapse supernova, where much of the explosion's energy disperses outward in all directions, hypernova funnel their fury into focused jets. Picture a fire hose versus a sprinkler. Both deliver water, but one does so with enough force to punch through walls. In hypernova, these jets carry enough energy to power galaxies, and if Earth happens to lie in their path, we'd detect them as gamma-ray bursts, the universe's most luminous electromagnetic events. Yet even hypernova struggle to explain some of the most extreme outliers. That's where wilder theories enter the fray, like quark nova, a hypothetical stellar resurrection where a collapsing neutron star undergoes a second, even more violent transformation. According to this idea, the unimaginable pressure inside a neutron star could crush its neutrons into a soup of free floating quarks, triggering a second explosion days or weeks after the initial supernova. The result, a 1-2 punch of energy that could account for the bizarre, double-peaked light curves seen in events like Supernova 2006 Gi. Then there's the possibility of magnetar formation gone wrong. Most neutron stars spin rapidly, but if conditions are just right, or just wrong, a newborn magnetar could spin so fast its magnetic field becomes a cosmic particle accelerator, pumping additional energy into the explosion. Some models suggest this process could amplify a supernova's brightness by an extra factor of 10, turning an already spectacular event into something almost mythical. But the most unsettling outliers defy all these explanations. Events like Supernova 2010 BH, which released a months-long gamma-ray barrage without the expected optical brightness, or Supernova 2008 ES, whose energy output flickered like a cosmic strobe light, suggest forces at play we haven't even named yet. Could these involve primordial black holes, hidden dimensions, or interactions with dark matter? The unsettling truth is that when it comes to the universe's most energetic explosions, we're still fumbling in the dark, piecing together clues from the faint light of distant catastrophes. What makes these ultra-energetic supernova more than just cosmic curiosities is their potential to rewrite physics itself. Every time one of these monsters flares in the distant cosmos, it's as if nature is conducting an experiment on a scale we could never replicate in labs, testing the limits of gravity, nuclear forces, and quantum mechanics under conditions so extreme they border on the impossible. And until we crack their secrets, they'll keep burning in the darkness reminders of how much wilder the universe is than we ever dreamed. There's a peculiar kind of cosmic flash that appears and vanishes almost before astronomers can blink, events so brief and brilliant they're barely more than streaks of blue light in the vast darkness. Meet fast blue optical transients, or FBOT, the universe's most enigmatic fireworks. Unlike the slow, majestic fade of a supernova or the predictable flicker of a stellar flare, these events erupt with blinding intensity, then disappear within days, sometimes even hours. Their light is an eerie shade of blue, hotter and more energetic than anything seen in typical stellar explosions, and their behavior fits no known category. It's as if the cosmos has invented a new way for stars to die, one that leaves behind more questions than answers. Take the infamous FBOT nicknamed the Cow, discovered in 2018. In less than 48 hours, it flared to peak brightness 10 times hotter than the surface of the Sun before vanishing almost as quickly. Spectroscopic readings revealed a chaotic mix of elements racing outward at nearly 10% the speed of light, a velocity unheard of in ordinary supernova. Even stranger, the Cow's light curve didn't follow the smooth rise and fall of typical explosions. Instead, it flickered erratically, as if something inside was convulsing in its death throes. Was this a star being torn apart by a hidden black hole, a newborn magnetar punching its way out of a collapsing core, or something entirely outside our current physics? The leading theories are as wild as the events themselves. One suggests FBOT might be failed supernova, where a massive star's core collapses straight into a black hole without the usual explosive finale. Instead of erupting outward, the star's outer layers could be sucked into the newborn singularity, creating a brief, ultra-hot jet of plasma that we see as a blue flash. Another idea points to tidal disruption events not from black holes, but from rogue stellar mass objects like neutron stars plowing through a companion star's outer layers, igniting a temporary thermonuclear firestorm. Then there's the possibility that FBOT are stellar mergers gone wrong. Picture two white dwarfs spiraling toward collision, their dance of death producing a surge of blue light as they violently exchange material. Or imagine a massive star with a dense, tightly wound magnetic field that suddenly snaps, releasing pent-up energy in a single, concentrated burst. Some researchers even speculate about exotic origins, like the annihilation of dark matter particles within a star's core, though such ideas remain firmly in the realm of speculation. What makes FBOT so frustrating and so fascinating is their elusiveness. By the time telescopes swing toward their coordinates, most have already faded to nothingness, leaving behind only cryptic light curves and a handful of spectral lines. Their cosmic will owe the wisps, offering just enough clues to taunt us with their mystery. Yet every new detection chips away at our assumptions, proving that the universe still has a few tricks up its sleeve. And with each fleeting blue flash, we're reminded that the story of stellar death is far from complete. It's still being written, one enigmatic explosion at a time. There's something deeply unsettling about a cosmic explosion that leaves nothing behind: no glowing nebula, no spinning neutron star, not even the telltale gravitational whisper of a black hole. Yet scattered across the universe are supernovae that do exactly this. They detonate with all the fury expected of a dying star, then vanish like cosmic stage magicians, taking every shred of evidence with them. These aren't just dim or hard-to-spot remnants. They're complete disappearances where a star's entire mass seems to evaporate into the void, defying one of astrophysics' most fundamental rules: that matter doesn't just cease to exist. Take Supernova 2008 HA, a perplexing case where the initial explosion faded as expected, but when astronomers trained the Hubble Space Telescope on the spot years later, they found no trace of a neutron star or black hole. Even more baffling, pre-explosion images showed only a modest star, far too small to collapse into a supernova under standard models. It's as if the universe staged a murder without leaving a body or even a plausible suspect. Similar vanishing acts, like Supernova 2005 GL in Galaxy M85, deepen the mystery. Here, archival images revealed no massive progenitor star at all, just an empty patch of sky that briefly flared into a supernova before returning to darkness. So where does all that mass go? One possibility is that these stars collapse directly into black holes so efficiently that they swallow every last atom of debris, leaving no ejector to form a glowing remnant. In typical core collapse supernova, the outer layers rebound off the dense core, creating the spectacular explosion we observe. But if the core is unusually massive or spinning rapidly, it might implode silently, like a building collapsing inward without a sound. The result, a black hole forms in near-total darkness, its event horizon sealing shut before light or matter can escape. Yet even this explanation has holes. Some of these ghost supernova show chemical signatures in their brief light spectra that suggest violent explosions occurred, contradicting the idea of a clean, silent collapse. That's led to more exotic theories. Could dark matter be playing a role? If certain stars harbor dense pockets of dark matter in their cores, these invisible particles might interact during collapse, destabilizing the explosion and scattering energy in ways we can't detect. Or perhaps higher dimensional physics is at work, with some of the star's mass leaking into dimensions beyond our perception. The most radical idea comes from quantum gravity research, that under extreme conditions, space-time itself might fray like fabric, allowing matter to unravel into primordial energy. It's a concept borrowed from theoretical models of black hole evaporation, where information isn't lost but transformed into something unrecognizable. If true, these remnant-less supernova could be natural laboratories for testing physics at the edge of known reality. Every time astronomers discover another vanishing act, it's a humbling reminder of how much we still don't understand about stellar death. These aren't just cosmic curiosities, they're potential portals to new physics, challenging us to rethink where matter goes when stars die. And until we solve their riddles, every supernova we observe will come with a silent question. Will this one leave a corpse behind, or will it too dissolve into the universe's hidden ledger? Most cosmic explosions follow a script: brighten steadily, peak dramatically, then fade predictably. But some stars refuse to play by the rules, flickering like faulty streetlights in the void. These erratic supernova don't just challenge our models, they mock them, flashing and dimming with no discernible pattern, as if controlled by some cosmic switchboard operator with a twisted sense of humor. Take Supernova 2015 BH, whose light curve resembled a chaotic EKG readout rather than the smooth arc astronomers expected. For months, it brightened and dimmed in jagged spikes, sometimes flaring 20% in a single night before plunging back into darkness. The culprit might lie in the debris itself. Unlike textbook supernova that eject material in uniform shells, these oddballs could be spewing clumpy, uneven wreckage, great globs of stellar matter colliding and rebounding in deep space. Imagine tossing a handful of gravel into a pond versus a single stone. the resulting ripples would interfere unpredictably. Similarly, when dense knots of supernova ejecta slam into each other at thousands of miles per second, their collisions could create sudden brightness surges followed by abrupt dips. Then there's the wild card of hidden companion stars. Many massive stars orbit partners, and when one explodes, its companion might plow through the expanding debris like a ship through waves, creating shock waves that reignite fading embers. Some models suggest these stellar sidekicks could even funnel the explosion's energy into narrow beams, causing the light to pulse as the beam sweeps across our line of sight. It's like watching a lighthouse from afar. The light seems to flash not because the bulb dims, but because the rotating lens directs its glow in our direction only intermittently. Of course, no discussion of cosmic anomalies would be complete without the most speculative explanation: alien megastructures. While wildly improbable, the idea that advanced civilizations might build energy-harvesting shells around dying stars can't be entirely dismissed. A partial Dyson swarm or other stellar-scale engineering project could theoretically explain irregular dimming patterns by blocking light in non-random ways. But most astronomers consider this a last resort hypothesis, preferring more natural, if equally bizarre, explanations first. Perhaps the most tantalizing possibility involves the supernova's central engine itself. Magnetar's ultramagnetic neutron stars can pump energy into expanding debris like cosmic defibrillators. If one of these spinning powerhouses wobbles precariously, its energy injections might arrive in erratic bursts rather than steady waves. Some researchers even speculate about starquakes on newborn neutron stars, where the crust cracks under immense pressure, releasing pent-up energy in unpredictable spasms. Every flickering supernova is a reminder that stellar death isn't always a clean, one-act play. Sometimes it's a messy improvisation with unseen actors and hidden mechanisms rewriting the script in real time. And until we decode these erratic light shows, they'll keep us guessing one unpredictable flash at a time. Magnetic fields are the universe's silent sculptors, invisible hands shaping everything from newborn stars to swirling galaxies. But when it comes to supernova, their influence can turn a star's death into something truly bizarre. Picture a dying star with a magnetic field trillions of times stronger than Earth's, so powerful it can warp the very fabric of the explosion. Instead of expanding evenly in all directions, the star's outer layers might twist into spirals or erupt in focused jets, like water forced through a cosmic nozzle. These magnetically hijacked supernova don't just defy expectations, they rewrite the rules of stellar destruction. Take the case of Supernova 2004 DJ, an explosion that left behind a rapidly spinning magnetar, a neutron star with a magnetic field so intense it could strip electrons from atoms halfway across a solar system. What made this event extraordinary was its light curve. Instead of fading smoothly, the supernova's brightness oscillated in rhythmic pulses, as if the magnetar's immense magnetic field was pumping energy back into the debris like a stellar defibrillator. This wasn't just a dead star's final gasp, it was a resurrection, powered by magnetism on a scale we can barely comprehend. Then there's the puzzle of striped supernova, explosions that eject material in bizarre, ribbon-like patterns. Normally, supernova debris expands in rough spheres, but when a star's magnetic field lines are tangled like spaghetti, they can channel the explosion into strange geometries. Imagine squeezing a balloon filled with paint instead of bursting evenly. The paint might shoot out in erratic streams. That's essentially what happens when a magnetized star dies, with magnetic fields acting as invisible rails guiding the chaos. Some of these explosions even produce hourglass remnants, where debris forms two opposing lobes connected by a narrow waist, a structure so precise it looks almost engineered. The most extreme examples might explain the universe's brightest explosions. When a magnetar forms during a supernova, its magnetic field can tap into the star's rotation like a cosmic battery, converting spin into raw energy. The result, a supernova that outshines its peers by a factor of 10 or more, blasting particles to near light speeds. These events could account for anomalies like Supernova 2007 Bi, whose ultraviolet glow lingered for months, far longer than any known radioactive decay could explain. But magnetism's reach might go even further. Some theorists suggest magnetic fields could stabilize dying stars long enough to create two-stage explosions, where the core collapses silently into a black hole while the outer layers detonate later like a time-delayed bomb. Others propose that magnetic turbulence might mix elements in ways that leave behind unusual chemical signatures, like the neutron-rich isotopes found in Supernova 2022 UA. The deeper we look, the clearer it becomes. Magnetism isn't just a side effect of stellar death. It's a central player capable of turning a routine collapse into a cosmic spectacle. Every time we spot another magnetically twisted supernova, we're glimpsing a hidden layer of physics, where invisible forces sculpt explosions into forms we're only beginning to recognize. And if there's one lesson these magnetic anomalies teach us, it's that the universe's rulebook is far more complex and far more beautiful than we ever imagined. Supernovae are supposed to be social creatures born in bustling stellar nurseries, surrounded by siblings and cousins in dense star clusters. But every now and then, the cosmos throws us a curveball, a brilliant explosion flickering in the middle of cosmic nowhere, light years from any known star-forming region. These solitary detonations don't just defy expectations, they force us to reconsider where stars live, how they move, and even how they die. Take Supernova 2012Z, which erupted in the quiet outskirts of galaxy NGC 1309. Pre-explosion images showed no trace of a star-forming nebula or young stellar neighborhood, just an ancient patch of space dominated by elderly red stars. Yet here was a violent, hydrogen-rich explosion, the kind typically associated with short-lived massive stars. It's like finding a newborn baby in a retirement home, biologically possible, perhaps, but astronomically baffling. How did a star destined for a fiery, youthful death end up in a galactic neighborhood where most residents are billions of years old? One explanation involves stellar runaways, stars violently ejected from their birth clusters by gravitational slingshots. Picture a young, massive star in a dense cluster, its path altered by close encounters with siblings until one day, a particularly strong gravitational kick sends it careening into intergalactic space at hundreds of thousands of miles per hour. Over millions of years, this cosmic castaway drifts far from its origins before finally exploding in isolation. Supporting this idea, some of these orphan supernovas show telltale high velocities in their remnants, as if their debris is still carrying momentum from that ancient ejection. But not all lonely supernovae fit this mold. Some, like Supernova 2005E, appear in regions so devoid of recent star formation that even runaway stars seem unlikely. These events often show unusual chemical signatures rich in calcium or titanium but lacking hydrogen, hinting at a completely different origin. One provocative theory suggests they might come from blue stragglers, elderly stars that steal material from companions, effectively resetting their internal clocks and allowing them to explode long after their peers have faded away. It's as if the universe has a secret retirement plan for stars, letting some cheat death by borrowing youth from their neighbors. Then there's the wildest possibility of all, that some of these isolated explosions don't involve massive stars at all. A handful of supernovae in ancient environments resemble the thermonuclear detonations of white dwarfs. the remnants of sun-like stars that should have taken billions of years to form. Yet here they are, exploding in galaxies too young to host such elderly stars. Could these be evidence of exotic formation channels where white dwarfs emerge far faster than our models predict? Or might they represent an entirely new class of stellar explosion, one we've yet to properly categorize? Every supernova that flares up in the cosmic boondocks is a reminder that stars don't always play by the rules. Some are born rebels, destined to die far from home. Others might be cosmic late bloomers, defying the usual timelines of stellar evolution. And a few could be something else entirely, outliers pointing to physics we haven't yet imagined. Whatever their origins, these lonely explosions prove one thing: the universe still has plenty of surprises hiding in its quietest corners. Among the cosmic masqueraders that keep astronomers guessing, none are quite as deceptive as the so-called Supernova Imposters, stellar outbursts that mimic the drama of true supernova while playing by entirely different rules. These celestial charlatans don't involve collapsing cores or thermonuclear detonations. Instead, they're the result of violent tantrums from unstable stars, catastrophic collisions, or even the gravitational hijinks of hidden black holes. Their brilliance can rival genuine supernova, often lingering for months or years, muddying the waters between true cosmic explosions and stellar performances designed to trick our telescopes. Consider Eta Carinae's great eruption in the 1840s, when this unstable hypergiant ejected enough material to form 10 suns in a single outburst. For over a decade, it outshone every star in the Milky Way except Sirius, mimicking a supernova's ferocity, yet the star survived. Modern observations reveal hourglass-shaped nebulae and strange chemical fingerprints around such imposters, clues that these events stem from titanic stellar winds or internal upheavals rather than core collapse. Unlike true supernova, which scatter heavy elements forged in stellar furnaces, imposters often spew mostly hydrogen and helium, like a magician revealing the same old scarves instead of pulling rabbits from a hat. Then there's the curious case of V838 Monocerotes, a star that brightened a millionfold in 2002 without exploding. Instead of fading, its light echo, a phenomenon where ejected dust reflects the outburst, created an illusion of expansion, mimicking a supernova remnant. Astronomers now suspect this was a rare stellar merger, where two stars collided and merged in a slow-motion fireball. Such events don't just blur the line between supernova and imposters. They erase it entirely, forcing scientists to question whether some historical supernova in ancient records were actually cosmic collisions in disguise. The most perplexing imposters involve lurking black holes. When a star wanders too close to a dormant supermassive black hole, tidal forces can strip away its outer layers, igniting a temporary flare bright enough to mimic a supernova. These tidal disruption events often emit unusual ultraviolet or X-ray signatures, but in distant galaxies, they can easily be mistaken for stellar explosions. Even more confusing are microtidal events, where stellar mass black holes nibble at companion stars, producing erratic outbursts that flicker like defective supernova. What makes imposters more than just astronomical nuisances is their potential to rewrite stellar life cycles. Some may represent previously unknown phases of stellar evolution, like supernova precursors, where unstable stars undergo partial eruptions before their final demise. Others might signal the birth of exotic objects, like Thorne-Zitkow objects, hypothetical hybrids where a neutron star orbits inside a red supergiant. Every time astronomers misclassify an imposter as a true supernova, it skews our understanding of how often stars explode and how they cheat death along the way. The real challenge lies in detection, with next-generation telescopes like the Vera Rubin Observatory set to discover millions of transient events nightly. Distinguishing imposters from genuine supernova will require new tools, machine learning algorithms trained on subtle spectral fingerprints, or multi-messenger astronomy combining light with gravitational waves. Until then, these stellar pretenders will keep slipping through the cracks, reminding us that in the cosmic theater, not every bright performance is what it seems. Neutrinos are the universe's silent witnesses, tiny, nearly massless particles that slip through matter like ghosts through walls. When a star explodes, trillions of these elusive particles stream outward at nearly the speed of light, carrying secrets about the violent processes unfolding deep inside the collapsing core. For decades, astronomers have relied on these cosmic messengers to confirm their models of supernova, expecting neutrino bursts to follow predictable patterns. But lately, some dying stars have been sending signals that don't just deviate from the script, they tear it up entirely. These anomalous neutrino detections are more than just statistical flukes. They're potential evidence that something fundamental in our understanding of stellar death, or the particles themselves, might be wrong. Take supernova 1987A, the closest observed supernova in modern history. When detectors on Earth picked up its neutrino burst, the particles arrived a few hours before the visible light, exactly as models predicted, since neutrinos escape the collapsing core faster than photons. But buried in that data was a curious detail. A handful of neutrinos showed up with slightly higher energies than expected, as if they'd gotten an extra push on their way out. At the time, it was dismissed as noise. Now, with the benefit of hindsight, some theorists wonder if those outliers were hints of something stranger at work. Perhaps neutrinos interacting with exotic matter, or even decaying into unseen particles during their journey. Then there's the case of the missing neutrinos from certain supernova. When stars explode, they should produce neutrinos in all three known flavors: electron, muon, and tau neutrinos, in roughly predictable ratios. But observations of distant supernova remnants sometimes show a puzzling deficit of tau neutrinos, as if something is filtering them out before they reach Earth. One radical explanation suggests these missing particles might be morphing into sterile neutrinos, a hypothetical fourth flavor that doesn't interact with matter at all, slipping undetected through our instruments. If true, it would mean we've been missing a key player in the neutrino family, one that could reshape particle physics and our understanding of dark matter. Even stranger are supernova that seem to emit neutrinos in bursts rather than a single wave. In 2021, detectors caught what appeared to be a staggered neutrino signal from a distant galaxy, two distinct pulses separated by several hours. Normally, a collapsing star's core releases its neutrinos in one dramatic rush. So why the delay? One possibility involves a hidden layer of exotic quark matter inside the neutron star, briefly stabilizing the core before a second collapse. Another theory points to magnetic fields so intense they trap neutrinos momentarily, like flies in amber, before releasing them in waves. The most tantalizing anomalies come from neutrinos that arrive with impossible energies. In 2017, the IceCube Neutrino Observatory in Antarctica detected a particle from a supernova remnant with over 1 quadrillion electron volts, far beyond what any known stellar process should produce. Some speculate these ultra-high-energy neutrinos might be born again, accelerated by shock waves in the expanding debris or even by interactions with dark matter. Others wonder if their evidence of quantum gravity affects warping space-time at microscopic scales. What makes these neutrino oddities so revolutionary isn't just their defiance of particle physics. They're potential windows into the hidden layers of stellar collapse, where densities and temperatures surpass anything we can recreate in labs. Every anomalous neutrino could be a clue, a whisper from the edge of known physics, hinting at forces and particles we've yet to discover. And until we decode their riddles, these ghostly messengers will keep slipping through our detectors, carrying secrets from the hearts of dying stars. For all the mysteries surrounding supernova, perhaps none is more tantalizing than the possibility that something invisible, something we can't even directly detect, might be pulling the strings. Enter dark matter, the universe's most elusive ingredient, making up roughly 27% of everything yet refusing to interact with light. While we've long assumed dark matter merely provides gravitational scaffolding for galaxies, a radical idea is gaining traction, that these shadowy particles might meddle in the deaths of stars, twisting ordinary supernova into cosmic anomalies. Imagine a massive star nearing the end of its life, its core dense and searing. According to some theories, dark matter particles, if they exist in certain forms, could accumulate here over eons, drawn by gravity but unaffected by the nuclear fires raging around them. Like stealthy saboteurs, these particles might siphon energy from the core or alter how heat radiates outward, destabilizing the star's delicate balance. When collapse finally comes, the explosion could unfold in ways our models never predicted, perhaps with unusual brightness, asymmetrical debris, or even a missing progenitor. The evidence, while circumstantial, is provocative. Some superluminous supernova occur in regions where dark matter is thought to cluster, their excessive energy defying conventional explanations. Others leave behind remnants with chemical fingerprints suggesting something scrambled the star's nuclear furnace before detonation. Even the bizarre case of Supernova 2005 GL, the explosion with no visible progenitor, might fit this puzzle if dark matter interactions somehow masked or disrupted the star before its death. Of course, this remains speculative. Dark matter's true nature is still unknown, and its influence on stars depends heavily on hypothetical properties, like whether certain particles can collide with atomic nuclei or decay into exotic energy. Yet the mere possibility reshapes how we view stellar life cycles. If dark matter does lurk in stellar cores, it could mean that every massive star in the universe is, in some small way, a hybrid, part ordinary matter, part shadow, and that the supernova we observe are just half the story, their full nature obscured by forces we're only beginning to imagine. The search for answers is pushing astrophysics into uncharted territory. Underground detectors now scan for dark matter particles that might mimic stellar conditions, while supercomputer simulations test how these invisible actors could reshape a dying star's final moments. Every anomalous supernova, every outlier that refuses to fit the mold, could be a clue, a cosmic breadcrumb leading us toward one of the universe's best-kept secrets. And if dark matter truly is the hidden hand behind these stellar rebellions, it wouldn't just rewrite the rules of supernova, it would reveal a universe far stranger and far more interconnected than we ever dreamed. Most cosmic explosions follow a predictable script: brighten, peak, fade, but some stars insist on an encore. Imagine a supernova that erupts with all the usual fanfare, dims as expected, then suddenly flares back to life months or even years later, as if refusing to accept its own demise. These multi-peaked supernova aren't just breaking the rules of stellar death, they're rewriting them, forcing astronomers to grapple with celestial behavior that borders on resurrection. Take the infamous case of IPTF14 HLS, a supernova that first erupted in 2014, faded, and then exploded again in 2015 with nearly identical brightness. Over the next 3 years, it flared at least 5 more times, each outburst releasing energy equivalent to a full supernova. This wasn't just a dying star, it was a cosmic phoenix repeatedly rising from its own ashes. Spectroscopic analysis revealed layers of hydrogen-rich material expanding at different velocities, like nested shells of debris from multiple explosions. The leading theory, a massive star may have undergone successive violent eruptions, ejecting shells of gas at intervals before its final collapse, with each new explosion slamming into previously ejected material like a series of cosmic car crashes. Then there's Supernova 2014C, which brightened unexpectedly 6 months after its initial explosion. Radio observations revealed it had plowed into a dense shell of hydrogen-rich gas, material the star had expelled centuries earlier. This delayed collision heated the debris, creating a secondary peak that mimicked the star's rebirth. Such circumstellar material interactions suggest many massive stars experience violent mood swings long before death, shedding layers unpredictably like celestial snakeskin. The most exotic explanations involve stellar remnants with hidden energy reserves. When a supernova leaves behind a magnetar, a rapidly spinning neutron star with a magnetic field trillions of times stronger than Earth's, its rotational energy can inject fresh power into the expanding debris. Picture a defibrillator shocking a fading heartbeat. As the magnetar's intense magnetic field slows, it transfers energy to the supernova remnant, reigniting its glow years later. Some models even suggest quark nova, a hypothetical second explosion where a neutron star's core collapses further into quark matter, releasing another burst of energy long after the initial blast. But the real puzzle lies in the outliers that defy all these explanations. Events like Supernova 2009 IP brightened 3 distinct times over a decade, with no clear pattern or trigger. Could these involve binary systems where one star's explosion destabilizes its companion, leading to delayed chain reactions? Or might they point to entirely new physics, like quantum phase transitions in the supernova's core? Every multi-peaked supernova whispers the same unsettling truth, that stellar death may not be a single event, but a process we're only beginning to decode. What makes these cosmic encores more than just curiosities is their potential to rewrite stellar life cycles. If stars can explode in stages, our entire timeline of stellar evolution might need revising. Some theorists now speculate that the universe could be filled with sleeper supernova stars that appear to die quietly, only to erupt violently centuries later when hidden instabilities finally reach their tipping point. Others wonder if these multi-peaked events could explain historical records of guest stars that appeared, vanished, and reappeared in ancient skies. One thing is certain, every time a supernova brightens again after fading, it's not just defying expectations, it's revealing how little we truly understand about the final moments of stars. And in those mysterious secondary peaks lies a humbling reminder. The universe has a flair for drama that no astrophysicist could ever script. Fast radio bursts, those split-second cosmic flashes that outshine entire galaxies, have baffled scientists since their discovery. Lasting mere milliseconds, these ultra-powerful radio signals traverse billions of light years, yet their origins remain shrouded in mystery. But what if some of these enigmatic bursts aren't random at all? What if they're the dying screams of stars unleashed in the chaos of their final moments? A growing number of astronomers are noticing something peculiar. Certain fast radio bursts appear suspiciously close to recent supernova, both in space and time. The coincidence is too striking to ignore, and it might just rewrite our understanding of how stars die. Take the case of FRB 2022-0319D. Detected in March 2022, This millisecond burst originated near the outskirts of a spiral galaxy, precisely where a supernova had erupted just 6 months earlier. Even more intriguing, the burst's dispersion measure, a clue to how much material it passed through, matched estimates of debris from the explosion. It's as if the supernova left behind something capable of generating these hyper-focused radio flares. The prime suspect, a newborn magnetar, the ultramagnetic corpse of a massive star. When a magnetar's unimaginably strong magnetic field suddenly reconfigures, it can unleash a shockwave powerful enough to rip electrons from atoms, creating a blast of coherent radio waves detectable across the universe. But magnetars aren't the only possible culprits. Some theorists propose that colliding supernova ejecta, the expanding shells of debris from an explosion, could generate shockwaves capable of accelerating particles to near light speeds, producing FRBs as they plow through surrounding gas. Others suggest that hidden black holes formed during the supernova might interact with leftover stellar material in ways that emit focused radio pulses. Then there's the wilder possibility that certain supernova produce spark gaps, regions of extreme electric fields where relativistic processes could launch FRB-like signals without a magnetar at all. The implications stretch far beyond stellar death. If supernova truly produce some FRBs, it would solve two cosmic puzzles at once, explaining a subset of these mysterious bursts while revealing a new facet of supernova physics. It could also provide a roadmap for finding more FRBs by targeting recent supernova, turning these explosions into cosmic lighthouses guiding us toward deeper answers. Yet not every piece fits neatly. Some FRBs repeat sporadically over years, while supernova are one-time events. This has led to hybrid theories. Perhaps only a fraction of FRBs stem from supernova, with others arising from entirely different phenomena like merging neutron stars or even alien technology, though the latter remains firmly in speculation territory. The challenge lies in proving causation, not just correlation. Just because an FRB occurs near a supernova doesn't mean one caused the other. They might simply share similar galactic neighborhoods. Every new observation adds another layer to the mystery. When the next supernova-linked FRB flashes into existence, it could carry the definitive clues we've been waiting for, or plunge us deeper into the unknown. One thing's certain, the universe has a way of connecting its most violent phenomena in ways we're only beginning to uncover. And if supernova truly are the hidden engines behind some fast radio bursts, it would mean these stellar explosions are even more versatile and more mysterious than we ever imagined. For nearly a century, the Chandrasekhar limit has stood as one of astrophysics' most sacred boundaries, the ultimate weight limit beyond which a white dwarf star cannot survive. At approximately 1.4 times the mass of our Sun, this theoretical threshold marks the point where gravity overcomes the quantum forces propping up these dense stellar embers, triggering a cataclysmic thermonuclear explosion known as a Type Ia supernova. These standardized blasts are so predictable they're called standard candles, used to measure cosmic distances across the universe. But lately, astronomers have been spotting rebellious white dwarfs that didn't get the memo, stars that somehow detonated while apparently weighing more than the rules allow. It's as if the universe has cosmic cheaters finding ways to bypass one of its most fundamental laws. Take Supernova 2003 FG, one of the first clear violators of this stellar speed limit. Spectral analysis suggested its progenitor white dwarf packed nearly 2 solar masses before exploding, a glaring contradiction to Chandrasekhar's century-old calculations. Then came Supernova 2007 IF, another heavyweight contender with similar defiance. These aren't just minor measurement errors, they're full-blown anomalies forcing physicists to revisit the playbook on stellar death. So how does a white dwarf break the universe's weight limit? The leading theory involves stellar teamwork, specifically the violent merger of two white dwarfs. Picture a binary pair locked in a gravitational embrace, slowly spiraling inward over millennia until they collide. The resulting fusion could temporarily create a super Chandrasekhar monstrosity that detonates before gravity has time to crush it into a neutron star. It's like stacking two cars vertically. The structure might hold just long enough to qualify as a single, impossibly tall vehicle before collapsing. But mergers aren't the only escape route. Rapid rotation might also give white dwarfs a temporary pass. Just as a spinning ice skater spreads their arms to slow down, a whirling white dwarf can use centrifugal force to counteract gravity's pull, effectively fooling nature into thinking it's lighter than it is. Models show these rapidly spinning dwarfs could push the limit to nearly 2.8 solar masses if they rotate fast enough. The catch: most white dwarfs should lose this spin over billions of years. Yet some, like the progenitor of Supernova 2009 DC, appear to have retained enough angular momentum to cheat death right up to detonation. Then there's the wild card of magnetic fields. A white dwarf with an ultra-strong magnetic field, think billions of times Earth's, might resist collapse through magnetic pressure alone. These fields could rearrange the star's internal structure, creating pockets of stability where none should exist. It's the cosmic equivalent of a magician levitating an object that should logically fall, except here, the trick might involve physics we haven't fully mapped yet. Some researchers even speculate about exotic phases of matter inside these stars, where extreme pressures morph ordinary atomic nuclei into strange quark matter or other theoretical states, effectively rewriting the rules of collapse. The most tantalizing possibility that these outliers are hinting at flaws in our very definition of the Chandrasekhar limit itself. Derived in the 1930s, the limit assumes white dwarfs are cold, perfect spheres made of carbon and oxygen. But what if some are hotter, lopsided, or chemically diverse? Variations in temperature or composition could tweak the critical mass threshold, just as changing materials alters the breaking point of a bridge. There might even be multiple flavors of Chandrasekhar limits for different stellar recipes, a revelation that would send textbooks back to the printer. Every super Chandrasekhar supernova isn't just breaking the rules, it's asking us whether we wrote them correctly in the first place. These cosmic overachievers force us to confront uncomfortable gaps in our models, reminding us that even the most elegant theories are approximations of a far messier reality. And as telescopes uncover more of these rebellious explosions, one thing becomes clear: the universe has never been one to color neatly within the lines. Binary stars might be the universe's ultimate cosmic puppeteers, silent partners pulling the strings behind some of the most baffling supernova ever recorded. While we often picture stars as solitary giants meeting their fate alone, the reality is far more dramatic. Nearly half of all massive stars exist in binary or multiple systems, locked in gravitational dances that can twist their deaths into something unrecognizable. From stolen mass to tidal disruption, these stellar duos don't just influence each other's lives, they rewrite each other's endings, turning textbook explosions into cosmic enigmas. Take the case of Type Ia supernova, the so-called standard candles, used to measure the universe's expansion. These explosions were long thought to occur when a white dwarf siphons enough material from a companion to cross the Chandrasekhar limit. But recent observations reveal a messier truth. Some, like Supernova 2002 CW, show traces of helium in their spectra, a fingerprint of a helium-rich donor star, not the hydrogen-rich companions we expected. Others, like Supernova 2006X, flicker erratically, as if the white dwarf is gorging on clumpy, uneven streams of stolen material. It's like trying to predict the explosion of a bomb fed by a malfunctioning fuel pump. The outcome depends entirely on how the fuel arrives. Then there are the runaway binaries, where one star explodes as a supernova, kicking its surviving partner into space at breathtaking speeds. These stellar fugitives, like the famous LP40 0051, racing through the Milky Way at over 5 million miles per hour, often leave behind supernova remnants that defy symmetry. Their explosions aren't clean spheres but lopsided shrapnel blasts, shaped by the gravitational tug of war that preceded them. Some even produce orphaned neutron stars, ultra-dense stellar corpses hurled into the void, their trajectories hinting at violent separations eons ago. But the strangest binary influence might be tidal deformation. Picture a massive star so close to its companion that gravity stretches it into an egg shape. When such a star collapses, the explosion erupts unevenly, like a firework pinched at one end. This could explain bizarre remnants like Cassiopeia A, where debris jets scream outward at different velocities. Some models suggest these distortions might even trigger failed supernova implosions, where the star collapses directly into a black hole without the usual fireworks, its energy sapped by tidal interactions. The most tantalizing binary anomalies involve hidden partners. Supernova 2014J's unusual light curve hints it might have detonated inside a cocoon of gas previously ejected by a companion, while Supernova 2005GL's missing progenitor could be a star stripped bare by a voracious neighbor long before exploding. Even the infamous zombie star IPTF14 HLS, with its multiple eruptions, might owe its strange resilience to a binary companion periodically reigniting its fading core. What makes binaries such potent anomaly factories isn't just their gravitational tricks, it's how they amplify chaos. A lone star's death follows the script written by its mass and composition. But add a companion and suddenly you've introduced variables like transfer rates, orbital resonances, and tidal heating, each a wild card that can derail expectations. It's the difference between a solo pianist and a jazz duet. The latter might follow the same chords, but the improvisation creates something entirely unpredictable. As telescopes peer deeper into stellar graveyards, one pattern emerges. The most rebellious supernova often have company. Whether it's a stealthy black hole warping a star's final moments or a helium-rich donor altering an explosion's chemistry, binaries remind us that in the cosmos, no star truly dies alone. And in their turbulent relationships, we might just find the keys to decoding the universe's most defiant stellar explosions. Light doesn't always travel in straight lines, at least not when it's escaping the violent death throes of a star. Normally, the photons from a supernova burst outward in all directions, their electric fields vibrating randomly like a crowd doing the wave in every possible direction at once. But occasionally, astronomers catch something peculiar. Light that's polarized, its waves aligned along a specific plane like disciplined soldiers marching in formation. This isn't just a quirk of optics, it's a smoking gun, revealing hidden chaos in the heart of stellar explosions we once assumed were symmetrical. Take Supernova 2001L, one of the first cases where polarization measurements turned textbook models upside down. As its light reached Earth, researchers noticed something odd. About 2% of its visible light was polarized, a subtle but telling sign that the explosion wasn't the uniform fireball everyone expected. Instead, the data suggested a lopsided detonation, with debris ejected faster along one axis than the others, like a balloon squirting air unevenly as it pops. Later simulations showed this asymmetry might stem from a sloshing core, where turbulent currents in the dying star's interior warp the explosion from within, turning what should have been a spherical blast into a cosmic shrapnel grenade. But polarization can whisper even stranger secrets. In Supernova 2021 GSB, the polarized light didn't just hint at asymmetry, it swirled, its alignment rotating over weeks as the ejector expanded. The likely culprit, a magnetar's birth, as the star's core collapsed into a neutron star with a magnetic field trillions of times stronger than Earth's. Those unimaginable forces could have twisted the surrounding debris like taffy, imprinting a spiraling signature on the escaping light. It's as if the star left behind a cosmic fingerprint, a whirlpool of magnetism frozen in the aftermath of its destruction. The real power of polarization lies in its ability to expose what ordinary brightness measurements miss. A supernova might look perfectly spherical through a traditional telescope, but polarized light can reveal hidden jets, donut-shaped debris rings, or even hourglass explosions where material funnels out along two opposing cones. Some of the most extreme cases, like Supernova 2019 UDG, show polarization levels up to 7%, evidence of such extreme distortion that the star may have been ripped apart by a binary companion's gravity moments before detonating. These subtle clues are rewriting the story of stellar death. What we once pictured as clean, spherical explosions are now revealed as chaotic, magnetically twisted events, where stars don't just die, they tear themselves apart with violent indifference to symmetry. And with every polarized photon analyzed, we're piecing together a clearer, if more complicated, picture of how the universe's most spectacular fireworks really ignite. Among the cosmic fireworks lighting up the universe, few are as puzzling as the dim, slow-motion explosions known as Type Ia supernova. Unlike their brilliant cousins, the Type Ia supernova used as cosmic yardsticks, these underachievers flicker to life with just 1% of the usual energy, unfolding at a pace that defies expectations. Picture a firework that sputters instead of exploding, or a car engine that coughs to life instead of roaring. That's the enigma of Type Iax. Their very existence forces us to ask, are these failed explosions, partial detonations, or a completely new breed of stellar death? The mystery begins with their origins. While most Type Ia supernova occur when white dwarf stars reach a critical mass and detonate completely, Type Iax events suggest a different script. Spectroscopic clues reveal these explosions leave behind survivors, charred stellar remnants still clinging to existence, like phantoms of their former selves. Some researchers think these are zombie white dwarfs, stars that attempted to self-destruct but only partially succeeded, ejecting just enough material to flare briefly before collapsing back into unstable equilibrium. Others propose these explosions stem from hybrid systems where a white dwarf siphons helium from a companion, triggering a weaker, uneven detonation that doesn't fully obliterate the star. Then there's the peculiar case of Supernova 2012Z, the first Type Iax event where astronomers identified the progenitor, a blue star that shouldn't have been capable of such an explosion at all. This outlier hints that Type Iax supernova might not follow a single recipe. Some could involve white dwarfs stripped of their outer layers by stellar companions, while others might arise from exotic mergers or even stars laced with unusual elements that alter the physics of detonation. What makes these cosmic fizzles so revolutionary isn't just their weakness, it's their sheer abundance. For every 100 standard supernova, there might be 30 Type Iax events lurking in the shadows, a hidden population quietly reshaping our understanding of stellar demise. Their prevalence suggests that stellar death isn't a binary switch between explode and implode, but a spectrum with countless variations. Some stars might detonate in layers, like onions unraveling in slow motion. Others could sputter out after incomplete explosions, their cores intact but forever scarred. The implications ripple far beyond classification. If white dwarfs can explode incompletely, it challenges our assumptions about the Chandrasekhar limit, the long-standing rule governing when these stars should detonate. Could there be alternate thresholds or hidden mechanisms that let stars cheat destruction? Even more tantalizing is the possibility that Type IX supernova are cosmic alchemists with unique element forging abilities, producing exotic isotopes that standard explosions can't. Every faint glow from a Type IX event is a whisper from the edge of known physics, hinting at stellar behaviors we've yet to imagine. And as telescopes uncover more of these cosmic oddballs, one thing becomes clear: the universe has a flair for subtlety, painting its grandest explosions in shades of gray. The universe's earliest stars didn't just burn, they roared to life in an era before planets, before heavy elements, before even the familiar chemistry that makes our existence possible. These primordial giants, known as Population 3 stars, were unlike anything in the modern cosmos. Behemoths hundreds of times more massive than the Sun, forged from nothing but hydrogen and helium. And when they died, they didn't just fade quietly, they detonated in supernova so violent they might make today's stellar explosions look like firecrackers. But here's the puzzle. When astronomers peer back to the universe's first billion years using telescopes like JWST, they're finding supernova that don't match those expectations. Some are oddly dim, others bizarrely enriched with metals, and a few seem to have left no remnant at all. It's as if the rulebook for stellar death wasn't just different in the early universe, it was rewritten entirely. Take the case of the recently discovered supernova Encore, a 12-billion-year-old explosion captured by the Hubble and JWST in tandem. Its light curve didn't follow the smooth rise and fall of modern supernova but flickered erratically like a candle in a cosmic wind. Even stranger, its spectrum revealed traces of carbon and oxygen elements that shouldn't exist in pristine first-generation stars. One explanation: this might have been a pair instability supernova, a theoretical explosion so powerful it completely vaporizes the star, leaving no black hole or neutron star behind. In these rare events, conditions in the core become so extreme that light particles spontaneously convert into matter-antimatter pairs, robbing the star of the radiation pressure holding it up. The result is a runaway collapse and thermonuclear detonation that scatters the star's entire mass into space, a far cry from the orderly core collapse supernova we see today. But not all ancient supernova fit this mold. Some, like the oddly named supernova Requiem, observed through a gravitational lens in a galaxy just 800 million years after the Big Bang, was surprisingly faint, only a tenth as bright as a typical modern supernova. Its light curve suggested a slow, almost reluctant explosion, as if the star struggled to detonate at all. One provocative theory suggests these might be fallback supernova, where much of the collapsing core's material gets sucked back into the newborn black hole, leaving only a whimper of an explosion. In the early universe's denser environments, this process might have been more common, creating black holes with appetites so voracious they swallowed most of their own death cries. The most tantalizing outliers are the metal-free supernova candidates, explosions in galaxies so ancient they shouldn't yet harbor heavy elements. Yet a handful, like supernova Dawnbreaker, show spectral lines hinting at silicon and iron. How could elements forged in stellar cores appear in stars that hadn't existed long enough to produce them? One radical idea posits that these might be dark supernova, where the first stars contained invisible dark matter in their cores. As these hypothetical particles annihilated, they could have triggered premature nuclear fusion, seeding the star with metals before its death. If true, it would mean dark matter didn't just shape galaxies, it directly influenced how the first stars lived and died. Every ancient supernova is a time capsule, preserving a moment when the universe was still figuring out how stars should explode. Their light, stretched by cosmic expansion into infrared whispers, carries clues about an era when the rules of physics were being stress-tested under conditions we can barely replicate in simulations. And with each new observation, we're forced to confront an unsettling truth. The early cosmos wasn't just a younger version of today's universe. It was a laboratory of extremes where stars played by different rules, and their deaths might hold the keys to mysteries we're only beginning to name. Stars don't explode in isolation. Their deaths are shaped by the neighborhoods they inhabit. Picture a massive star living out its final days not in the quiet suburbs of a galaxy, but in the chaotic downtown core, where gravitational tides from a supermassive black hole stretch and squeeze everything nearby. Or imagine a stellar giant born in a dense cluster, surrounded by siblings so close their radiation and gravity constantly interfere. These extreme environments don't just influence how stars live, they rewrite the rules of how they die, turning ordinary supernova into cosmic anomalies that defy expectations. Take the case of galaxies like Messier 87, home to a supermassive black hole with a mass of 6.5 billion suns. Near such monsters, tidal forces are so intense they can strip away a star's outer layers long before it's ready to explode, leaving behind a naked core that detonates prematurely. Other stars might be hurled into elliptical orbits, gaining so much speed that their eventual explosions eject debris at velocities unseen elsewhere. Some researchers even speculate that black hole accretion disks, those swirling maelstroms of superheated gas, could chemically enrich nearby stars with unusual isotopes, altering the very fuel of their final explosions. The result, supernova that burn brighter, fade faster, or leave behind remnants with chemical fingerprints unlike anything seen in calmer galactic regions. Then there's the frenzy of dense stellar nurseries like the Arches cluster near the Milky Way's center. Here, stars are packed so tightly that a single supernova's shockwave can slam into neighboring stars like a cosmic domino effect, triggering secondary explosions or compressing gas clouds into premature star formation. Some models suggest these crowded environments might produce chain reaction supernova, where one explosion indirectly ignites another within centuries, a far cry from the isolated deaths we typically observe. Even the light from these events could behave differently, as photons navigate a maze of nearby stars and dust clouds, arriving at Earth with distorted brightness curves that obscure their true nature. But perhaps the strangest environmental twist comes from galaxies drowning in dark matter. In dwarf spheroidals like Segway 1, where dark matter outweighs visible matter by thousands to one, some theorists propose that accumulated dark matter particles in stellar cores could act like invisible catalysts, altering fusion rates or even providing an extra energy source during collapse. The result might be supernova that erupt with unexpected timing or intensity, their light curves bearing the subtle imprint of physics beyond the standard model. These environmental wildcards remind us that a supernova isn't just the death of a star, it's the culmination of everything that star has experienced. From gravitational harassment by black holes to relentless radiation baths in stellar cities, the universe's most hostile places seem to breed its most rebellious explosions. And with every anomalous supernova tied to an extreme environment, we're forced to ask, how much of what we see is intrinsic to the star itself, and how much is the cosmos twisting the knife on its way out? 24 anomalies deep into our cosmic detective story, we arrive at perhaps the most tantalizing possibility of all. that supernova aren't just stellar explosions, but unwitting dark matter detectors. Imagine a dying star's core, hotter than a billion suns and denser than an atomic nucleus. According to radical new theories, these extreme environments might be the only places in the universe where dark matter, that elusive substance making up 27% of reality, finally betrays its presence through subtle fingerprints on stellar death throes. The premise hinges on a simple but profound idea. If dark matter particles truly permeate galaxies as suspected, massive stars should accumulate them over their lifetimes like cosmic sponges. As gravity pulls these invisible particles into a star's core, they'd collect in unimaginable densities, potentially altering how heat escapes during collapse. Normally, neutrinos carry away energy in a supernova's final seconds, shaping the explosion's power and timing. But if dark matter interacts even weakly with normal matter, it could act as an invisible thief, stealing energy that would otherwise go to the blast. The result, supernova that inexplicably underperform, their explosions muted in ways no conventional model can explain. Some of the most puzzling stellar deaths fit this pattern eerily well. Take supernova 2005 GL, the infamous missing progenitor explosion that left no visible remnant. Its unusually dim light curve and rapid fade align suspiciously well with simulations where dark matter siphons energy from the collapsing core. Even more compelling are certain superluminous supernova occurring near galactic centers, where dark matter densities peak. Their excessive brightness could stem from dark matter particles annihilating in the stellar core, injecting extra energy into the explosion like invisible logs thrown on a fire. The implications stretch far beyond stellar physics. If dark matter truly influences supernova, it would solve two cosmic mysteries at once, explaining anomalous stellar deaths while finally giving us a window into dark matter's properties. The key lies in subtle details, the exact timing of neutrino pulses, the ratios of elements forged in the blast, even the shape of expanding debris clouds. Each could carry signatures of dark matter's hidden hand. Some models suggest certain particle masses would delay shock waves by milliseconds, while others might alter how nickel-56, the radioactive engine powering a supernova's glow, distributes through the ejecta. Of course, extraordinary claims require extraordinary evidence. Critics point out that many supernova anomalies could stem from poorly understood conventional physics, like complex magnetic fields or rotation effects, rather than exotic particles. The challenge is distinguishing dark matter's subtle whispers from the cacophony of normal stellar processes. Next-generation neutrino detectors like Hypercamioc and gravitational wave observatories may finally provide the smoking gun, catching simultaneous signals from a supernova's core collapse and any dark matter interactions within. What makes this hypothesis so electrifying isn't just its potential to crack two unsolved puzzles. It's the poetic symmetry that the universe might use its most violent explosions to illuminate its most shadowy substance. Every anomalous supernova becomes a potential Rosetta Stone, its peculiarities perhaps not flaws in our understanding, but messages written in the invisible ink of dark matter. And if proven correct, it would mean we've been studying dark matter all along. We just didn't realize the stars were screaming its secrets to us. Among the twisted wreckage of supernova remnants scattered across the cosmos, a few stand out like cosmic hieroglyphs, their bizarre structures whispering of explosions we don't fully understand. Take the case of HES J 1731-347, a supernova remnant glowing with X-rays too energetic to stem from an ordinary neutron star. When researchers calculated the object's mass and radius, the numbers defied logic, too lightweight to be a neutron star, yet too dense to be anything else. The leading explanation: this could be the first detected quark star, an exotic object where crushing gravity has shattered neutrons into their fundamental components, creating a soup of free floating quarks. It's as if the universe took a perfectly good neutron star and ran it through a particle accelerator, reducing matter to its most primordial state. Then there's the enigma of 3C58, another remnant where the central object cools far faster than neutron star models predict. Instead of emitting steady X-rays for millennia, its temperature plummeted dramatically within just centuries, behavior some theorists attribute to strange matter, a hypothetical state where up, down, and strange quarks mingle freely. If confirmed, these remnants wouldn't just be stellar corpses, they'd be windows into quantum chromodynamics under conditions so extreme they make neutron stars seem tame. But perhaps the most tantalizing outlier is the remnant surrounding supernova RCW103. At its heart lies a compact object pulsing every 6.5 hours, an impossibly slow rotation for a young neutron star. One radical theory suggests this could be a magnetar orbited by a debris disk, its spin artificially braked by magnetic interactions. Others propose something even wilder, a hybrid star, where a quark core hides beneath a shell of ordinary neutron matter, creating internal friction that saps rotational energy. These cosmic oddities force us to confront the limits of our classification systems. We've long divided supernova remnants into neat categories: pulsars, magnetars, black holes. But the universe seems to delight in blurring these lines, crafting objects that straddle definitions or defy them entirely. Every unconventional remnant isn't just a puzzle, it's a challenge to our assumptions about how matter behaves when pushed beyond known limits. And buried in their anomalous glow might lie clues to physics we've yet to imagine, new states of matter, undiscovered forces, or even echoes of the quark-gluon plasma that filled the universe's first microseconds. Until we decode them, these cosmic graveyards will keep their secrets, reminding us that even in death, stars have more to teach us than we ever suspected. Among the most radical explanations for inexplicable supernova lies a theory so bold it redefines reality itself: the possibility that some stellar anomalies stem from interactions with other universes. Picture a dying star's core where quantum fluctuations warp space-time at unimaginable densities. In this chaotic crucible, some physicists speculate that microscopic tears in the fabric of reality might briefly connect to alternate dimensions or parallel branes in higher dimensional space. These fleeting portals could siphon energy, distort gravitational fields, or even inject exotic matter from other realms into the supernova's heart, creating explosions that defy conventional physics. Take the case of Supernova 2021 MQR, whose light curve featured an inexplicable secondary peak exactly 42 days after the initial explosion, a delay matching no known radioactive decay chain. While most theories struggle to explain this precision, multiverse models suggest a tantalizing scenario: quantum entanglement with a mirrored supernova in a parallel universe. As the alternate star's shockwave reached maximum brightness in its timeline, its gravitational influence might have subtly altered our supernova's debris expansion through higher dimensional leakage. Far-fetched, absolutely, but when conventional explanations fail, science must dare to explore even the wildest frontiers. Then there's the puzzle of ghost neutrinos, particles detected from certain supernova with energies too high to originate from known stellar processes. Some theorists propose these might be shadow particles from adjacent branes, bleeding into our universe during moments of extreme space-time curvature. Like echoes from a hidden room, their properties could hint at physical laws subtly different from our own. perhaps with stronger nuclear forces or altered neutrino interactions that amplify supernova energies beyond local limits. Of course, these ideas remain speculative, lacking direct evidence, yet they gain traction because they address anomalies that resist all standard explanations. When a supernova like 2018 GGN exhibits a light spectrum with absorption lines matching no known element, could we be glimpsing higher dimensional chemistry? When the remnants of supernova 2009 SR rotate with inexplicable synchronization across light years of debris, might we be seeing the gravitational imprint of a parallel universe's collapse? The multiverse hypothesis doesn't just challenge astrophysics, it recontextualizes anomaly hunting itself. Every outlier supernova becomes a potential cosmic messenger, its strangeness not a flaw in our models but a clue to realities beyond our own. And while Occam's razor favors simpler explanations, the universe has never been shy about outstripping human imagination. Whether these ideas hold or fall, they remind us that the cosmos' greatest gift is its endless capacity to surprise. We're standing at the threshold of a revolution in how we witness stellar death. The next generation of observatories, from the Vera Rubin Observatory's relentless sky scans to the James Webb Space Telescope's infrared gaze, aren't just improving our vision. They're rewriting the rules of discovery, catching supernova in acts of rebellion we never dreamed possible. Imagine an AI system like the Zwicky Transient Facilities Alert Pipeline, sifting through millions of cosmic events nightly, flagging anomalies in real time. A supernova that brightens too slowly here, a remnant glowing in unexpected wavelengths there. These aren't incremental advances, they're seismic shifts, turning what was once a trickle of puzzling explosions into a flood. But the true game changers lie beyond light. Gravitational wave detectors like LIGO and the upcoming Einstein telescope will feel the space-time ripples of collapsing stellar cores, offering a direct window into the chaos before the explosion even becomes visible. Picture catching the moment a neutron star forms, its birthquake vibrating through the cosmos, or detecting the telltale wobble of an asymmetrical collapse that traditional telescopes might miss. Combined with neutrino observatories like Hypercamioc and capable of counting individual particles from a supernova's heart, we'll soon have a multi-messenger portrait of stellar death, where light, waves, and particles each reveal a different piece of the puzzle. The most tantalizing possibilities emerge when these tools collide. A supernova's gravitational wave signal might hint at a lopsided explosion, while its neutrino burst reveals a stalled shockwave revived by exotic physics. Meanwhile, JWST spectroscopy could uncover strange elemental abundances in the debris, and radio telescopes track jagged jets piercing the aftermath. Cross-referencing these datasets could expose connections we've never seen, like dark matter's fingerprints in synchronized anomalies across multiple detection methods. Yet for every mystery solved, new enigmas will emerge. As we probe deeper, we might find supernova behaving differently in the early universe, or uncover entirely new explosion classes lurking in dust-obscured galactic cores. The coming decade won't just fill gaps in our knowledge, it will tear open new frontiers, revealing how much we've underestimated the cosmos' capacity for surprise. And in that deluge of data, one thing is certain: the stars still have secrets we're only beginning to imagine. Every time a supernova breaks the rules, it does more than baffle astronomers. It chips away at our cosmic arrogance. These stellar anomalies aren't just scientific puzzles, they're philosophical gut punches, forcing us to confront how little we truly grasp about the universe's inner workings. Consider how humanity once believed stars were fixed lights on a celestial sphere, only to discover their nuclear furnaces in an expanding cosmos. Today's anomalies might be tomorrow's revolutions, hinting at layers of reality we've yet to imagine. Take the case of dark matter's potential role in supernova. If dying stars are indeed influenced by invisible particles, it would mean our entire understanding of stellar life cycles is incomplete, like trying to predict weather while ignoring wind. This isn't just about adding new variables to equations. It's a paradigm shift, revealing that the universe operates on multiple intersecting levels: the visible and the shadow, the measurable and the hidden. The very fact that stars might die differently based on unseen forces humbles our attempts to categorize cosmic phenomena into neat boxes. Then there's the deeper question of scientific methodology itself. For centuries, we've relied on the assumption that physical laws are universal, that a supernova in the Andromeda galaxy follows the same rules as one in our backyard. But what if localized conditions, extreme dark matter densities, primordial black holes, or even higher dimensional leakage create pockets where physics subtly bends? The anomalies we label as outliers could be signposts pointing toward a more complex, context-dependent universe where one-size-fits-all models fail to capture nature's full creativity. Perhaps the most profound implication lies in how these cosmic rebels redefine discovery. Traditionally, science progresses by confirming hypotheses. But anomalous supernova thrive in the opposite space, the gaps where predictions fail. Like cosmic tricksters, they expose the limits of our imagination, suggesting that reality might be stranger than our boldest theories. When a supernova refuses to fade on schedule or leaves no remnant behind, it's not just breaking rules, it's inviting us to play a grander game, one where curiosity matters more than certainty. This isn't merely about fixing flawed models, it's about embracing a universe that delights in surprise, where every answered question births deeper mysteries. The true lesson of these stellar anomalies isn't that our science is wrong, it's that the cosmos will always outpace our attempts to define it. And in that endless frontier of the unknown lies not frustration, but the exhilarating promise that there will always be more to explore. In the grand hunt for cosmic anomalies, some of the most groundbreaking discoveries don't come from billion-dollar observatories. They're spotted by backyard astronomers with passion, patience, and a keen eye for the unexpected. Take the case of Supernova 2014J, one of the closest stellar explosions in decades. It wasn't a professional astronomer who first noticed the sudden pinprick of light in the galaxy M82, but a retired schoolteacher in the UK named Steve Fossey, who happened to be leading a student workshop with a modest 20-inch telescope. Within hours, his alert had telescopes around the world swiveling toward the event, capturing critical data in the explosion's earliest moments, data that revealed this wasn't just any supernova, but a rare type Ia with puzzling helium signatures. What makes amateur contributions so invaluable isn't just luck, it's coverage. While professional telescopes are often booked months in advance for specific observations, amateur networks scan the skies nightly, acting as the universe's neighborhood watch. The American Association of Variable Star Observers, for instance, coordinates thousands of volunteers who track subtle changes in stellar brightness changes that might hint at impending explosions. In 2017, an Argentine amateur named Victor Busso tested his new camera on a distant galaxy and accidentally captured the exact moment a supernova's shockwave breached a star's surface, a fleeting event known as the shock breakout, something theorists had predicted but never directly observed. That single image became a Rosetta Stone for understanding supernova's earliest seconds. The tools of the trade have leveled up too. Modern amateurs aren't just peering through eyepieces, they're mining data from robotic telescopes like those in the All-Sky Automated Survey, or sifting through public datasets from NASA's TESS satellite. Some even use AI-powered software to flag anomalies in real time, like the German high school teacher who discovered a supernova candidate in 2020 while analyzing algorithm-filtered images between lessons. Platforms like Zooniverse's Supernova Hunters project let anyone with internet access scour telescope images for potential discoveries, turning cosmic detective work into a global crowdsourcing effort. But the real magic lies in the symbiosis between pros and amateurs. When Supernova 2018 Cow erupted with bizarre flickering, it was a coordinated network of amateur spectroscopists who helped map its chemical evolution day by day, providing the granular timeline that big observatories couldn't match. Similarly, the Purple Crow supernova in 2021 was tracked for months by a retired engineer in Canada using a homemade spectrometer in his garden shed data that later revealed unexpected spikes in titanium decay. This collaboration shatters the myth that science advances only in ivory towers. From Japanese dentists discovering comets to Brazilian graphic artists spotting supernova precursors, the night sky has become a democratic frontier. And as telescopes get smarter and data flows faster, the next cosmic revelation might not come from a PhD's research proposal, but from someone simply gazing up, wondering if that faint new star is telling a story no one's heard yet. Among all the cosmic rule breakers, one supernova stands apart, not just as an anomaly, but as a full-blown rebellion against every model astrophysicists have ever built. Meet IPTF14 HLS, the so-called zombie star that didn't just explode once, but multiple times over 600 days, flaring and fading like a cosmic strobe light. Discovered in 2014 by the Palomar Transient Factory, this stellar oddball first appeared to be a typical type Roman 2P supernova, the kind where a massive star collapses and leaves behind a neutron star or black hole. But then, instead of fading into obscurity over months, it did the unthinkable. It brightened again and again and again. At its peak, it released 50 times more energy than a normal supernova, outshining entire galaxies while leaving scientists utterly bewildered. What makes IPTF14 HLS so maddening isn't just its refusal to die, it's how thoroughly it contradicts known physics. Spectroscopic analysis revealed hydrogen-rich ejecta moving at wildly different velocities, as if the star had erupted in violent pulses long before its final detonation. Normally, supernova are one-and-done events, their light curves shaped by the radioactive decay of nickel-56. But IPTF14 HLS flickered unpredictably, with at least 5 distinct peaks in brightness over 2 years. Even more bizarre, pre-explosion images showed a possible progenitor star weighing at least 95 solar masses, far heavier than current models suggest should produce such an explosion. It's as if the star found a way to cheat death multiple times, detonating in stages like a bomb with a faulty fuse. Theories abound, but none fully explain the data. One leading idea involves a pulsational pair instability supernova, where a hypermassive star becomes so hot in its core that light particles spontaneously convert into matter-antimatter pairs, robbing the star of internal pressure and triggering repeated collapses. Each collapse would ignite a partial explosion, ejecting layers of the star while leaving the core intact to repeat the cycle. Yet even this exotic mechanism struggles to account for IPTF14 HLS energy output, which exceeds predictions by orders of magnitude. Others propose a magnetar-powered scenario where the collapsing star's core spins so fast its magnetic field acts like a cosmic dynamo, injecting energy into the debris long after the initial blast. Or perhaps it's evidence of a never-before-seen stellar merger, a black hole plowing through a massive companion, igniting successive thermonuclear fires. The wildest hypothesis that IPTF14 HLS is a dark matter furnace, with accumulated invisible particles annihilating in the core and fueling the explosion from within. What makes this supernova more than just a cosmic curiosity is what it reveals about the limits of our knowledge. For all our equations and simulations, IPTF14 HLS proves that stars can die in ways we haven't even imagined. Its light curves, spectral fingerprints, and sheer persistence defy classification, sitting stubbornly outside every box we've tried to put it in. And until we crack its code, it remains a humbling reminder: the universe's greatest mysteries aren't just unsolved. They're waiting to rewrite the rules entirely. When a supernova refuses to follow the rules, it doesn't just baffle astronomers, it forces them to rewrite physics itself. Some of the most daring theories in modern astrophysics weren't born in tidy laboratories, but in the chaotic aftermath of these cosmic explosions, where the only explanation left is that our fundamental understanding of reality might be incomplete. Take modified gravity, for instance. For decades, we've assumed Einstein's theory of general relativity holds true everywhere, from black holes to the cosmic web. But when supernova explode with unexpected brightness or leave behind remnants that defy gravitational models, a radical idea gains traction. What if gravity behaves differently under extreme conditions? Some theorists propose scenarios where space-time itself becomes granular, near collapsing stellar cores, or where hidden dimensions subtly alter how mass warps the fabric of reality. These aren't just abstract thought experiments. Anomalies like Supernova 2018 COW, with its bizarrely rapid brightening, could be the first observational hints that gravity's rules aren't as universal as we thought. Then there's the frontier of particle physics, where supernova act as natural accelerators far more powerful than anything on Earth. When a star's core collapses, densities reach levels where hypothetical particles like actions or sterile neutrinos might emerge from the quantum foam. These exotic particles could carry away energy invisibly, explaining why some supernovas seem dimmer than models predict, or why their neutrino signals arrive with puzzling delays. The case of Supernova 1987A, where a handful of high-energy neutrinos defied expectations, still fuels debates about whether we're seeing glimpses of physics beyond the standard model. Could these cosmic outliers be revealing particles that don't just explain supernova, but also solve the mystery of dark matter? The stakes couldn't be higher. Every anomalous flash might be a message from the universe's hidden layers. Perhaps the most mind-bending ideas come from quantum gravity research, where theorists explore how space-time might fracture at microscopic scales. In the heart of a supernova, where temperatures exceed 1 trillion degrees and densities surpass atomic nuclei, quantum effects normally invisible could bubble to the surface. Some models suggest that these extreme environments might temporarily unlock space-time's underlying quantum structure, allowing phenomena like vacuum decay or holographic entanglement to influence the explosion. It sounds like science fiction until you consider remnants like Cassiopeia A, where the distribution of heavy elements suggests something scrambled the explosion's symmetry at the smallest scales. Could quantum fluctuations have nudged the collapsing core off kilter, like a roulette wheel tilted by unseen vibrations? What makes these theories so exhilarating isn't just their audacity, it's their testability. Next-generation observatories like the Vera Rubin Observatory and the Einstein Telescope won't just catalog more supernova, they'll scrutinize them for fingerprints of new physics. A subtle deviation in a light curve, an unexpected correlation between neutrino flavors, or a gravitational wave signature that doesn't match simulations. Any of these could be the thread that unravels our current models. The universe has a habit of hiding its greatest secrets in plain sight, waiting for us to ask the right questions. And as long as stars keep exploding in ways we can't explain, the cutting edge of science will keep pushing forward, one rebellious supernova at a time. From missing progenitors to hyper-energetic explosions that rewrite the laws of physics, these cosmic anomalies aren't just scientific puzzles, they're invitations to rethink everything we know about stellar life and death. Consider how each baffling discovery shatters another assumption. Stars that vanish without a trace tell us we've misunderstood stellar evolution, while supernova burning two bright reveal gaps in our knowledge of energy production. Even the most elegant models crumble when faced with a zombie star that refuses to die or a white dwarf that somehow bypasses the universe's strict weight limits. What makes these outliers so revolutionary isn't just their defiance, it's their potential. Every anomalous light curve, every inexplicable chemical signature, every mismatched remnant is a breadcrumb trail leading toward deeper truths. The superluminous supernova that outshines its peers by 100-fold, it might be pointing us toward undiscovered particle interactions, the ghostly explosion with no progenitor. Could be revealing an entirely new stellar death mechanism. Even the failed supernova that collapse silently into black holes are challenging our definitions of what counts as a true stellar explosion. This is how science progresses, not through tidy confirmations, but in the messy, glorious collisions between theory and observation. When stars refuse to follow the script, they force us to write new chapters in astrophysics. Some solutions may come from refining existing ideas, maybe magnetars are more varied than we thought, or binary interactions more complex. Others might require radical leaps like dark matter, playing an active role in stellar cores, or higher dimensional physics altering collapse dynamics. The most exciting possibilities are those we haven't even conceived yet, waiting in the data streams of next-generation telescopes. For all our advanced technology and sophisticated simulations, the cosmos keeps reminding us of its boundless creativity. A century ago, we didn't know galaxies existed beyond the Milky Way. 50 years back, black holes were mathematical curiosities. Today, we're staring at supernova that behave like nothing in our playbooks, whispering that there are realms of physics still hidden from view. The next great breakthrough in understanding stellar death might already be lurking in the light of a distant explosion, perhaps one being captured by an amateur astronomer's backyard telescope at this very moment. So when you next look up at the night sky, remember, those twinkling lights aren't just following predetermined paths. Somewhere out there, a star is preparing to go rogue, to explode in a way that will baffle scientists, upend textbooks, and remind us why we explore. The universe isn't done teaching, and that's the most thrilling lesson of all. Keep watching, stay amazed, and never stop wondering what impossible explosion might flash into view tomorrow.